So in my next derivation, we are going to calculate the packing efficiency in hexagonal close packing and that of your cubic close packing. Remember, the packing efficiency in both of these close packings is almost the same and is also known as that of your face-centered cubic. Face-centered cubic. We know that in the face-centered cubic, the atoms will be present at the corners and also at the 6 faces of the cube. Let me once again say you, in all the derivations, we are just deriving the packing efficiency. In order to have a clear knowledge of what do you mean by this packing efficiency, I have given my earlier example. One more time I am saying it. If you are having a plastic cover, for example, and you are putting a Fanta bottle in it, of course the plastic cover will not acquire, the Fanta bottle will not acquire the overall plastic cover. Instead, some space will be left empty. So what is the space that Fanta bottle is covering in that plastic cover? That will be called as a packing efficiency. Here also the same way. If you are taking a unit cell and you are knowing how much atoms are present in it, what will be the total space will be covered by all those atoms? That will be said as that of your packing efficiency. So let us now go on with this derivation of the packing efficiency in a HCP and a CCP, which is also called as that of your face-centered cubic. As mentioned earlier, it's like I'm just taking any one face for my derivation to be in an easier manner without any ambiguity. Okay, so like this, I have drawn my unit cell. So what we know, our atoms are present at the corners, please do remember, and also they are present at one of the face. Yeah, like this. Able to see? So that means what? In a face-centered cubic, they will be present at the corners and also the 6 faces of your cube. Just I have taken one face for my derivation to be a easy one. I will be taking the same naming as A, B, C, D, E, F, G and a H. Of course, from here also I am drawing a diagonal, okay, which is going to that of your centers. Let me call this one as that of your B. So here, of course, the edge lengths are that is equals to A, since here also I have chosen my cube itself, okay, in all the cases. So first of all, let us choose a triangle now. I am choosing a triangle of that of your A, B and C. I am choosing a triangle of A, B and C. So from the triangle ABC, what we can say, AC square, of course, AC square is equals to what? AB square plus BC square. AB square plus BC square. Of course, I have said they are all having the edge lengths A, so here also A, here also A. So AC square is equals to how much? It is equals to B square. So that is equals to AB square is A square plus A square. So B square is equals to 2 times of your A square. Let me just check the value of B. B will be equals to root 2 into A. Let me keep this much itself. Of course, here B is also, I have mentioned earlier, what will be the value of B. So in the earlier expression, we choose that as a C. And we came to know that C is equals to 4R. Here also the same expression, considering the radius, 1R, 2R, 3R, 4R. So B is equals to what? 4R. So substituting in the equation 1, how can you write it? 4R is equals to root 2 into A. So now we have to determine the value of your A. So A will be equals to what you can write? Yes, I can write it as 4 by root 2 into R. Can write in this way? Yes or no? In simple words, I could write this 4 as how? Can you see? 4 can be written as 2 into 2 divided by that of your root 2. Yes, so that is into R. This 2 can be written as how, if I'm just writing as root 2 square, can I write it? Yes or no? I'm just taking for what will be having root 2 square, this square and this square root gets cancelled, so you'll be getting as 2 itself. So 1, 2 I'll be writing as root 2 square into 2r, of course this 2 I am keeping as it is, this 2r, divided by root 2. So 1 square and 1 root 2 gets cancels. So what will be getting as the value of a? A is equals to root 2 into 2r, or in simple words, if you follow 2 root 2 r. Anyway you can just write. Able to understand? So we are getting the a value as 4 by root 2 into r. This 4 can be written as 2 into 2. 2 2s are 4. I have just chosen for 1 2 I have written as root 2 square, because root 2 square is nothing other than that of your 2 itself. So taking that root 2 square into 2r divided by this root 2, root 2 gets cancels, 1 root 2 is left over, so a is obtained as 2 root 2 r. Is that clear? So once you have got the value of your a, now let us go with the packing efficiency. We want what in packing efficiency? Number of atoms in that unit cell. So what is the number of atoms in our face-centered cubic? We have calculated from the 8 corners we will be getting 1 atom, and from the 6 faces 6 into 1 by 2, that is equals to 3. Overall you will be getting as 4 atoms. So number of the atoms is 4. Is that clear? So from the definition of the packing efficiency, you have to write the in derivation, you have to write the formula again and again. So what will be obtained? Volume occupied by the 4 spheres now. Volume occupied by 4 spheres in the unit cell, of course, divided by total volume of unit cell. That is what total volume of unit cell means. Unit cell is like your cube, so it will be equals to a cube into 100. So of course volume occupied by 4 spheres means 4 spheres are there, and each sphere is having a volume of 4 by 3 pi r cube. So 4 into 4 by 3 pi r cube. Total volume of the unit cell means a cube. Here what you have got the value of a as 2 root 2 r. So a cube can be written as how? 2 root 2 r the whole cube. Able to understand? So when you are just solving it, we are getting the value as 74%. Able to understand what I have done over here? So 74% for that of your HCP and a CCP, that is when you are considering that of your face-centered cubic lattice, only 74% of the space is covered by all the atoms present in this unit cell. Whereas in a body-centered, it was just 68%. Whereas when coming with respect to that of your hexagonal close packing or cubic close packing, we are getting the packing efficiency equals to that of your 74%. That means what? When you are choosing all the atoms to be present in this cubic unit cell and also at the face-centered, the total space which will be covered by all the atoms will be equals to 74%, which will be that of the packing efficiency of your face-centered cubic lattice, which is greater than that of your body-centered cubic lattice.